Hello, everyone. Welcome to another episode of Q&A about science and technology for kids and others. Let's see, I am not in my natural habitat today, so strange things could go wrong. But let's hope for the best. All right, let me see. I have a bunch of questions here. Ooh, where should we start? There's a question here from Lola. How do galaxies form? Well, it's not completely known, but here's the first thing to say. Gravity tends to always pull things together. So if you have matter, that if you have any kind of material, it will tend to get clumped together by gravity. Now, if things were completely uniform, there's no way for it to know kind of where to start to clump. Once there's a place where there's more material than elsewhere, that place where there's more material the material will start to get pulled together, and it'll get more and more material in the place where there was already more material. So it's kind of like the winner is going to take all, so to speak. But the question of how one gets an initial situation where it's not completely uniform, that's not so obvious. And it's been kind of a mystery how that works in the very, very early universe. Because kind of you would imagine that the universe, when it first starts off, there'd be no way to distinguish one part of the universe from another. You might imagine the universe would be completely uniform, completely homogeneous. But in order to have a place where there is what's usually called the density perturbation, a place where there's a higher density of material than other places, there has to be something non-uniform going on. So there are a bunch of theories about the very, very early universe that talk about why there would be that kind of inhomogeneity forming. There's some pretty wild theories. I guess I was involved in some of them back in the late 1970s, actually. I never really quite believed in these theories, but they've become quite widely accepted in the years since. I have to say, I think in recent times, our understanding of the discrete structure of space probably gives one an idea of why, in the end, the universe can't have been completely uniform. Because once you think that space is discrete, there are places where there's sort of an atom of spaces, and the atoms of space are discrete. So you can never get something which is just completely uniform density, because there'll always be an atom of space there, not an atom of space there, and so on. So I think there's in our very recent understanding of kind of the discrete structure of space, there's some way to understand why the universe wouldn't be just completely uniform density. Once there are density perturbations, non-uniformities in density, the places where there's more density of material get clumped up by gravity, and they start forming larger and larger kind of areas of clumping. So now the idea that people have is that galaxies formed from places where there was sort of a place where there was a higher density, bigger clump, and then when there wasn't such a big clump, all the material from that area would get pulled into the galaxy area and out of the area sort of between the galaxies. When did that happen? Well, the universe is about 14.5 billion years old now. Probably there's sort of a big discussion right now as people try to see what were the earliest galaxies that can be seen from the James Webb Space Telescope, for example. You can kind of tell how old the galaxy was from using information about the expansion of the universe. You can kind of tell when a galaxy was formed by essentially how fast it's going away from us in the expansion of the universe. It takes a little bit of thinking to understand why things that are sort of where the light started longer ago correspond to things where they are receding from us at higher rates. But that's the way it works. And so you can kind of use that to get some measurement of sort of how old the galaxy was. And there was a claim a little while ago that maybe there were galaxies that formed within a few hundred million years of the beginning of the universe. I think that's really short, and probably it was actually a bit longer than that. But essentially what had to happen was for sort of clumps of density to form that would turn into galaxies. Now, one of the interesting questions is galaxies are not uniform in the universe. There are about 100 billion galaxies in the universe, And they are the galaxies, in addition to the material in the galaxy being all clumped to form galaxy versus the space between the galaxies, also the galaxies themselves are in clumps. So our galaxy is part of a cluster of galaxies, and there's a lot more empty space between clusters of galaxies than there is within clusters of galaxies. And so this whole question of what's the distribution of galaxies in the universe and how much clumping is there, and all sorts of features have been observed, kind of great walls of galaxies and all kinds of places where there are gaps and so on. And that probably is giving one a big clue about how galaxies were originally formed in the very, very early universe. Once one has kind of a galaxy, once one has one of these density perturbations, it will grow, and there are different kinds of galaxies of different sizes. And as one looks at the sort of the spectrum of density perturbations, there are probably some bigger perturbations, smaller perturbations. Some of them form different kinds of galaxies. Our galaxy is a spiral galaxy. It's a fairly big galaxy. And it has the feature that when things were kind of condensing to form, when things were getting sort of pulled together to clump together to form our galaxy, there was a certain amount of angular momentum, a certain amount of spinning around that was happening. And as things got pulled closer in, that the amount of kind of spinning increased. Things started spinning faster, because that's just what happens with, it's kind of like when you're spinning around, you put your arms out and you pull your arms in, you'll spin around faster when you pull your arms in, because you're conserving angular momentum. And the only way to do that, where the angular momentum is essentially the distance multiplied by the rate of spinning. And so as you decrease the distance by moving your arms in, you'll spin faster. Same thing happens with galaxies as they get smaller when they're sort of clumping together. And so they start spinning around, and that produces kind of the spiral, the flattened spiral galaxy form that a galaxy like ours, or the Andromeda galaxy, which we can see, has. And the way, so there are other galaxies, smaller galaxies, and things called globular clusters. There are a couple of those that are in orbit around our galaxy, the Magellanic Clouds, which are more sort of spherical lumps of stars, considerably smaller than our galaxy, that didn't have this kind of spinning and flattening phenomenon. But then there are all kinds of other things that happen in the formation of galaxies, not yet completely well understood. Like there's a central black hole that forms as kind of the giant garbage dump in the middle of the galaxy, pulling stars in. The one in our galaxy is about 100,000 times the mass of the sun, and it's gradually pulling material from our galaxy into it. Other galaxies have bigger and smaller black holes at the center, and that's probably something to do with the age of the galaxies and such like. But that's kind of roughly how galaxies form. The role of dark matter in the formation of galaxies is not yet very well understood. What one observes in our galaxy, for example, is that the rotation of the galaxy, one could sort of work out how fast things should be rotating and so on, based on kind of the gravitational attraction associated with the galaxy. And what happens is that when you do that calculation, the amount of sort of gravitational attraction is larger than you can account for on the basis of the stars that you can see in the galaxy. So it's as if there's something dark, in other words, not producing light like stars, but still having an effect, a gravitational effect. And so it's been that phenomenon has been known for nearly 100 years now. And there's sort of this question of, well, what is that phenomenon? What is it? Is it a change in the laws of gravity? Is it something where there's some kind of matter that is some matter that we can't detect? What really is that? The name that's emerged for this is dark matter, kind of prejudging the answer and saying it really is matter, but it's just matter that isn't luminous like stars. I happen to think that that's probably not the right explanation, and that probably dark matter, with matter in quotes, is more a feature of the structure of space and details of the structure of space and its effect on gravity, rather than something that can be thought of as matter and particles like electrons and things like this. Anyway, a few thoughts on the formation of galaxies. There's still quite a bit that is not known about how material that is sort of being attracted through gravity behaves on a large scale. See, when you have like molecules in a gas, Or if you were to take sort of all the gas in a room and stick it all in one corner, we know that pretty soon the gas, just through random collisions of the molecules, the gas will fill the room roughly uniformly. And that's a feature of, that's the second law of thermodynamics that is kind of telling one that sort of what starts as something very kind of organized will tend to randomize. And so, for example, the gas will fill the room. But if the gas is self-gravitating, if that gas consists of, like, let's scale it up really big and say the gas consists of stars that all have gravity that's pulling the stars together, then that phenomenon of the second law and sort of the idea that things will uniformly fill the space is no longer true. In fact, that's exactly why things like galaxies form, because gravitational forces clump things together. They sort of do that in apparent violation of the second law of thermodynamics. It's exactly how that really works, and whether sort of what's really going on is that in the structure of the gravitational field and the structure of kind of the forces that pull those stars together, that there's sort of there's more kind of information, randomness, and so on associated with that field that's kind of compensating for the fact that the stars are being clumped together in an organized way. That's kind of one way to understand what's going on, but it's a somewhat complicated set of issues that really haven't been fully resolved. And by the way, the other piece to that gets complicated is that black holes are very, in some sense, very kind of uniform. You have a black hole, it's kind of, you can think of it as a perfect sphere, and the only features that it has are a certain mass and a certain spin rate and so on. But then there's a notion of kind of a way in which there's entropy, randomness associated with black holes. And that has to do with the way that black holes produce particles and interact with particles. And anyway, this is a slightly more complicated story, which probably doesn't have much relevance to the thinking about the relationship between thermodynamics, the dynamics of things that are associated with heat. Heat is associated with the sort of random motion of molecules. Thermodynamics is a sort of a story of the dynamics of heat, and the sort of thermodynamics of self-gravitating systems, something I've been interested in for a super long time, but it's still a rather messy, unresolved area. Let me give you an example of why it gets really complicated. Okay, so you might think you've got all these kind of stars, they're kind of interacting, they're colliding, they're interacting according to gravity. When you have molecules in a gas, they can hit each other and they basically bounce off. When you have stars, they kind of hit each other and they're not going to bounce off. They're going to end up in a clump, probably. But what can happen is the stars can go very close to each other, and when they go very close to each other, the gravitational force is very high. There's an inverse square law of gravitational forces, and that means when r is big, 1 over r squared is small, but when r is small, 1 over r squared can be very big. So that means that the gravitational force associated with stars that just sort of graze each other, that almost kind of collide, but just avoid colliding by just a tiny amount, the gravitational forces associated with that can be quite large. And you can end up with a star that ends up with very high energy because it kind of slingshotted around another star and gets sort of gets pushed with very high energy. That's one thing that can happen. Another thing that can happen is those two stars can get close to each other and they can make a binary star system. They can just make something which is always clumped together as a pair of stars. Both of those things make for a lot of trouble in kind of analyzing sort of the as if it was gas molecules, kind of uniform, the tendency of kind of gases to become more uniform. And they're both places where self-gravitating gases really differ from other gases in terms of their kind of overall behavior. Let's see. Gosh. There's a question here from Tool4. Is it true that animals can sense earthquakes? How? Why can't humans? Well, I don't know if animals can sense earthquakes. People sometimes say that. I mean, people also will say, when it's about to rain, the cows will lie on the ground, will go on sit on the ground type thing. What are these animals noticing that we're not? Well, for example, in the case of the cows and rain and so on, maybe they're sensing humidity, maybe they're sensing the air pressure. These are things which perhaps we could teach ourselves to directly sense humidity. I mean, one can tell when it's more humid, one tends to sweat more and things like this. Maybe one can tell about the air pressure. Certainly, if you've got on a plane and you take a bottle of water, plastic bottle or something, and the pressure in when the plane is at its altitude is the water bottle will expand, and then when if you open it on the plane and then you come back down to sea level, then the bottle will be crushed, and your ears will pop and things as if the pressure in the plane changes rapidly and such like. So there are ways in which sort of slightly indirect ways in which we can sense air pressure. So those are two things which are more like, is it going to rain type questions, which we're probably not usually all that sensitive to, but one can imagine with our ordinary senses, so to speak, being sensitive to those things. Now, the main things that one suspects might lead animals other than us to be able to detect impending earthquakes are electric and magnetic fields, probably particularly electric fields. So the issue is when an earthquake is going to happen, there's lots of stress in rocks. That's what makes the earthquake end up slipping as opposed to sticking, is there's so much pressure that builds up, so much stress in the rocks, so much internal force that eventually the one part of the plates that make up the rock in the earth will slide relative to the other. So one of the things that happens when rock is under high pressure, can happen, is that it produces electric fields. Roughly the reason that happens is that normally in an atom, there is, the atomic nucleus, protons, neutrons, and so on, that's positively charged. Then there are electrons, those are negatively charged, and those things perfectly balance each other. But there is an effect where if you crush the rock enough, you can kind of get the electrons to move relative to the nuclei in the atoms just a bit. And the result of that is that you have kind of an electric field that you have kind of essentially electric charge that is uncancelled a bit in the rock, and that leads to an electric field. And so then the question is, well, can animals sense electric fields? We can't directly. When there's from the surface of the Earth up to clouds and so on, there is as we go from the Earth, there is a gradient of voltage leading to an electric field that always exists. When there's a thunderstorm, for example, and when you're going to have the lightning strike comes because there is effectively a high electric field, such a high electric field, eventually the electric field is large enough that it causes breakdown in the air. It's an electric field that is so strong that it will pull the electrons and the nuclei of atoms apart. It will make the atoms effectively lose their electrons, and then that's what allows one to have this trail of ionization, turning atoms into ions that corresponds to a lightning strike. So when there's when there's a large electric field, eventually the air will break down. You'll get lightning strikes and so on. People sometimes say that when there are earthquakes about to happen, that you see kind of lightning type strikes near the ground. I don't know if that's really true, but so in any case, the basic point is when the rocks are being crushed a lot, there is the possibility that they will produce electric fields which are larger than the ordinary electric fields that exist on the surface of the Earth. And then the question is, well, can animals detect those things? Well, I don't know. There certainly are animals which can detect electric fields. For example, there are fish that produce electric eels produce electricity, and they sense that. They use some of that to. They have a way. Oh gosh, how does this work? they're using electrical pulses to be able to detect the presence of things around them, and they have sensors that detect those electric fields as a way to detect things that are around them in the water and so on. And so I don't exactly know how those sensors work, although one can imagine that electric fields affect the electrochemistry of a bunch of the sensors that exist in skin and so on. Essentially, well, the way nerve cells always work is by chemical processes that lead to electrical effects. Just like a battery, for example, has chemical processes that lead to an electrical effect of producing a voltage and a current and so on. The same is true. That's how all nerve cells work. And that's, one can imagine, when you put an electric field on such a cell, that it can then have an effect on that cell that would be detectable as something that you can sense. So I think the sort of the likely possibility would be that if the animals are noticing there's an earthquake going to happen, it's that they're noticing that the electric field has gotten stronger. Whether there are magnetic fields associated with earthquakes, I'm not sure. The question of whether one can sense a magnetic field is another interesting question. There's pretty good evidence that pigeons sense the Earth's magnetic field, and that helps them to navigate, because they know kind of which way is north, because the Earth's magnetic field goes sort of from some place near the South Pole to some place near the North Pole. There's magnetic field lines that are going between those, and the sort of prevailing theory of how one senses magnetic fields in a pigeon's brain or something like this is actually pretty tricky, and involves kind of an atom with a certain spin which is affected by the magnetic field, trapped in a kind of a cage in a protein, but able to affect the sort of chemistry of the protein. And it's a place where kind of it seems like one can potentially detect what amount to quantum mechanical effects directly in a way so that brains, in this case pigeon brains, can detect them. Whether there are magnetic fields associated with earthquakes, I'm not sure, but if there were, then the expectation would be that it's this kind of atom in a protein trap that can detect those kinds of things. Now, by the way, that sort of idea of a quantum mechanical effect in biology is sort of generalized in modern times to the possibility of making quantum sensors very sensitive ways of measuring magnetic field. And that's kind of one of the interesting directions for applying quantum mechanics, making better navigation devices, things like this, by using the very sensitive way in which one can measure magnetic fields through these kinds of effects. Let's see. Weasel is commenting, I always found it fascinating how birds pick up those fields to get directions of where to fly. Yeah, I think one of the weird ones is that I think there is evidence also that one way birds manage to navigate is by following roads, which is kind of a less impressive, in some sense, mechanism than having some special quantum mechanical thing in their brains. Walrus is commenting, people with joint pain can often sense air pressure and humidity changes. Yes, I should have mentioned that. And some develop a sense for when the weather will change as a result. Yes, indeed, I should have mentioned that. I mean, I think that let's see, why does that happen? That happens because the cartilage, I think, I wonder why that really happens. I mean, it's probably because there's a pressure change in the fluid, the joint fluid, synovial fluid or whatever, relative to the air pressure. That the joint is sealed, and so the fluid inside it has a constant pressure, but the air pressure outside is changing, and so that produces forces inside the joint, which are then sensed by nerves that are nearby, and that's why you end up getting pain in joints. Would be my guess. Um, let's see. Question here from Grace saying, question from a science class. What is the difference between speed and acceleration? Let's see if I can explain that. So imagine your very, very simple level. You're going in a car and you're going from place A to place B and you're going at 30 miles an hour. That's saying in 1 hour, you will have traveled 30 miles. You're going at a speed of 30 miles per hour. Now the question is, if you're just starting from being stationary and you want to accelerate to 30 miles an hour, you might take, I don't know, 10 seconds to accelerate. That's a very long time. It's a kind of a crummy car, I think. That accelerate from 0 miles an hour to 30 miles an hour. So acceleration is changing speed. Speed is changing position. So when you say you're going at 30 miles per hour, you're changing your position such that in an hour, you will have changed your position by 30 miles. Acceleration, you're changing your speed. So you would say you're going from 0 to 30 miles an hour in 10 seconds, for example. That's telling you you're changing your speed over 10 seconds. You change your speed from 0 miles per hour to 30 miles an hour. So sort of a very famous kind of acceleration is the acceleration due to gravity, which is about 9.8 meters per second per second. So speed is measured in units of, let's say, miles per hour or meters per second. That's telling you how much distance did you go in a certain amount of time. Acceleration is how quickly did you change your speed. So, for example, when you drop an object, assuming you don't have air resistance, the speed of that object will change by 9.8 meters per second per second. So after 1 second, if you just let it go and it has 0 speed at the beginning, after 1 second, it will be going 9.8 meters per second, and so on. So kind of that's the idea that speed is a change of position with time. Acceleration is a change of speed with time. You can ask, well, what's the next thing up? The next thing up is usually called jerk. That's the change of acceleration with time. And so that's the if you're going from no acceleration. So when you have, let's say you're accelerating and you're always accelerating at a uniform rate. So imagine you're in a car or a plane or something or a rocket, and it's accelerating at a uniform rate. You'll be sort of pushed back in your seat, let's say, if it's accelerating forwards, and that amount of pushing back, the amount of pushing back depends on the acceleration. Actually, I should explain an important point here, which is there's an equivalence between acceleration and the effect of gravity. So I mentioned that there's an acceleration due to gravity. You drop an object, it will accelerate by about, on the surface of the Earth, by about 9.8 meters per second per second. There's sort of a big question of whether the effect of that acceleration is kind of like the force of gravity. So let's take an example. Let's say you're in an elevator, all the windows are blocked off, and the elevator is moving up. And the question is, can you tell that it's acceleration of the elevator, or could it be the case that somehow you got transported to a planet that has higher gravitational force, acceleration, and where there's more gravity there, and it's just that there's more gravity? So put another way, if you're in space where far away from the Earth, let's say there's no gravity pulling you to the Earth, but you start accelerating, then if you accelerate by 9.8 meters per second, it will be as if you were being sort of pulled down to the surface of the Earth to a surface at that rate. So, for example, for spacecraft, for instance, if you're on a trip to Mars and you want to have sort of artificial gravity, you can get that by having sort of continual acceleration. And by the way, you can have continual acceleration by just going in a circle, because as you go in a circle, you're always having to change. But if you go in a circle, okay, if you're going in a straight line at a certain speed, then you keep a constant speed. But if you want to go in a circle, you have to change your speed or you have to change your velocity, because the velocity is a speed in a certain direction and you're changing the direction. So for example, by the time you're on the opposite side of a circle, if you're going around, whatever you were originally going at a certain speed in one direction, by the time you're on the opposite side of the circle, you're going at that speed in the opposite direction. And so to get from one velocity on one side of the circle to the velocity on the other side of the circle, you have to have acceleration. And whenever you're sort of going around in a circle, there is acceleration associated with that. And that acceleration you can use that in principle. If you have a spacecraft that's kind of rotating, then you can use that acceleration to make yourself kind of an artificial gravity. And if you rotate at the right speed, I think there are all kinds of parameters about how big the spacecraft has to be able to rotate at the right speed and so on. You can simulate more or less the gravity of the Earth. But in any case, there's this equivalence between acceleration and the effects of gravity. It's called the principle of equivalence. It was a thing that Einstein came up with around just before 1915, I guess. And it's something which has actually been very accurately verified by looking at the motion of the moon. It's known that within one part in a it must be one part in 1,000 trillion, that acceleration has the same effect as the force of gravity. So in any case, that means that if when you are accelerating in a car that's accelerating at a uniform rate, you're kind of being pushed back into your seat as if you were kind of being pulled by gravity back into your seat, and that might be you could achieve that by having tipped yourself so that you're kind of lying on your back or something and being pulled down by the gravity of the Earth. But in any case, so when you're in uniform acceleration, that means that the rate of acceleration is not the acceleration is not changing, and then you kind of feel like you're just being pulled back to a certain force. If the acceleration changes, then it feels different from that. It feels like you're being kind of jerked around. And so this notion of what's called jerk is the change of acceleration with time. It's like, well, you were just getting pulled back in your seat, but then the acceleration changes and you're pushed forward again and pushed back again and so on. That's what is usually called jerk. Now, in the world of calculus, all of these things are sort of connected. So position, you can call it x, some quantity x as a function of time. You say there's a certain position, and then you say, what's the rate of change of position with time? Sometimes called x dot or x prime. Well, x dot would be speed, velocity. That's the change of position with time. And x double dot will be the change of position with time. That's acceleration. X triple dot is the jerk, the change of position with time. And that's a little bit of an attempt to explain how speed and acceleration are related. Let's see. There's another question here from Grace, another question from a science class. If energy is conserved, how do we run out of it? Okay, let's see. Well, first point is about energy conservation. So there are different forms of energy. So One form of energy, very commonly observed one, is kinetic energy, the energy associated with things moving around. And there's just a formula that says, at least for things moving reasonably slowly, that if the mass of a thing is m and the velocity is v, then the kinetic energy is a half mv squared. So that's one form of energy. And you can, if you have, when, for example, one thing that's moving runs into another thing that's moving, assuming that there was no heat generated and it was all perfectly elastic and so on, the total energy is conserved. So that means if there's one thing that's really big and has a high mass and it's barreling along with a certain velocity and it hits a bunch of things that are maybe of lower mass, those things of lower mass, in order to conserve energy, if the big thing is brought to rest, those smaller things have to go much faster, because that formula says if it's a half mv squared, if their mass is smaller, to compensate for that, their v has to be bigger. So conservation of energy, conservation of kinetic energy tells one, assuming that everything is elastic, it's not, we'll come to that in a minute, then it's kind of telling one, it's giving one some constraints on the velocity of different things and how the velocity of one thing relates to velocities of other things and so on. It goes along with momentum conservation. Momentum is mass times velocity, but between momentum conservation and energy conservation, that puts many constraints on kind of how things can move and so on. So that's kinetic energy. But kinetic energy is not the only form of energy. Kinetic energy, when you have a thing with kinetic energy, you're saying the whole thing is moving. Like all the atoms in the thing are all going in the same direction at a certain speed. And that gives it kinetic energy. Another form of energy is heat. What is heat? Well, heat is not sort of the whole thing has all its atoms going in the same direction. Instead, heat is lots of atoms moving around very quickly, but they're moving in random directions inside the thing. And as you heat the thing up, they move faster. And what happens is that each individual atom has kinetic energy. Each individual molecule has kinetic energy. And the heat energy of the material is the sum of all those kinetic energies of the individual molecules. So the individual molecules are running around all kinds of random ways, and each one of them has a certain energy. And then the energy of the material, the heat energy of the material, is the total of all those individual kinetic energies. But when you heat something up, the thing doesn't just all start moving. There's motion inside the thing at the level of molecules, but the thing itself might just sit still. So kinetic energy is associated with the organized motion of sort of all atoms going in the same direction. Heat is energy where the energy is the motion of individual molecules, but they're all moving around randomly. This is actually the story of the second law of thermodynamics, that it tends to be the case that when you start with organized kinetic energy, it tends to degrade into heat. So, for example, a good example of that is friction. When you might have organized motion, you're moving something relative to something else, and it's kind of just scraping along, and the result of it scraping along is it generates heat. The individual molecules at those surfaces are getting moved around randomly, and it generates heat. And so the energy that was associated, the kinetic energy that was associated with moving the thing, that kinetic energy is now dissipated as heat. The kinetic energy turns into heat energy. So the claim about conservation of energy is that the sum of all those different kinds of energy is constant. Now, those are two kinds of energy, kinetic energy and heat energy. Those are two typical forms of energy. There are other forms of energy. So another energy is potential energy, which is, for example, when you move things in a gravitational field, you can move them. When you put things higher up, they have higher potential energy. You hold the thing very high up and then you let it go, and it will get kinetic energy. How does it get kinetic energy? It gets kinetic energy by sort of making use of the acceleration due to gravity. And in effect, as it gets kinetic energy, it's taking energy away from the gravitational field. It's taking energy. In the end, it's moving the Earth just a little bit, but because the Earth is really, really heavy relative to the object itself, doesn't have any measurable effect on the Earth. But that motion is what is making it changes potential energy into kinetic energy. So places where that's used a lot, like a hydroelectric dam, for example, there's lots of potential energy because there's a lot of water that's high up on one side of the dam, and then that gets turned into kinetic energy as the water rolls down through the dam and through the turbines that make electricity inside the dam. So that's another form of energy, is potential energy. There are other forms of energy like chemical energy. Chemical energy is energy associated with the binding together of atoms into molecules. And let's see, so the way to understand this, let's think how to explain this. The different forms of energy, chemical energy, nuclear energy, these are associated with, well, let me see. I guess the right way, all right, there's a couple of other tricky issues to deal with. The basic point is that if you have, let's see, when we think about, potential energy and so on, let's say we have a spring and we're pulling the spring apart. The spring, and there's energy associated with the spring, which if we let the spring go, the objects at the ends of the spring will start moving, so they get kinetic energy. And the energy that's effectively stored in the spring, the energy that's associated with it's energy associated with the kind of distortion of the spring. Now how does that happen? What's actually going on there? What's going on? Okay, so when you have a material, a solid, for example, there are atoms that are being the thing is a solid because the atoms are being pulled together by forces between atoms. As you pull the atoms apart, it takes how to explain this? This is always very bad when there are things where this is kind of the official physics explanation of this is something I've known for well over half a century, and it's easy to kind of say the words associated with this, but to try and explain it from first principles is not so easy as I'm realizing here. But the basic point is that let me explain it the sort of official physics way. You can talk about things like binding energy. And that's a way of saying when things like with a spring, when the spring is kind of not pulled apart, there's no energy associated with the spring itself. As you pull the spring apart, there's a bunch of energy associated with the spring itself. And that energy you can think of as being associated with you're always at energy. You're kind of working against forces that try and pull atoms together, which try and make the solid a certain size, make the spring a certain size. As you pull against those forces, you're using energy to pull against those forces, and that's the thing that you're kind of getting when you pull the spring apart. You're getting it within the spring. There's energy. Okay, so how does this work in the case of chemistry? What happens is that if you have something like gasoline, for example, like like some kind of molecule that has a bunch of carbons, a bunch of hydrogens, and so on, there's a certain what's basically happening is there's a certain energy that is kind of like the spring is kind of stored in the binding of those carbons and hydrogens together. And when you burn that material, for example, when you add oxygen, you oxidize that material, you're breaking apart those bonds, you're breaking the carbons and hydrogens apart and so on. And as you break them apart, you are essentially releasing the energy that was associated with those bonds. When the molecule was originally formed, it took energy to form the molecule, but that energy then was sitting sort of inside the molecule, just like it takes energy to pull the spring apart. But once you have the spring apart, if you just carry around the spring pulled apart, there's energy associated with the spring, with the spring being in that state. And if you ever release the spring, you'll turn that energy back into kinetic energy. So when material like petroleum or something, or these hydrocarbons were formed, there was energy required to make these molecules, to get them into this structure, and that energy is then stored inside those molecules and released when you burn those molecules. Okay, so one of the principles that seems to be true in physics is that overall energy, with all these different forms of energy, they can be converted into each other by, for example, kinetic energy converted into heat energy. You can convert potential energy to kinetic energy to potential energy. All these different forms of energy can be converted into each other. But in the end, there's a way of saying that the total energy in any form is conserved. Now, we haven't known in the past sort of why energy is conserved in the universe. We have a little bit of a better idea from our models of fundamental physics that we've developed in the last few years. And maybe I shouldn't describe that, but there's a kind of very fundamental interpretation of energy in terms of thinking about the microscopic structure of space and energy being associated with essentially the rate of activity in the microscopic structure of space. And from that, you can effectively derive energy conservation, which is something that in the past, in thinking about physics, there hasn't really been a way to derive energy conservation. It's just been an assumption about the way physics works. Little footnote about energy conservation. On a very, very large scale of the whole universe, energy conservation doesn't really work the same way. Because, among other things, the universe is expanding, and that expansion you can think of as having been initiated by sort of lots of energy put into the universe at the beginning, but you can trade off expansion of the universe. You can kind of make use of that expansion to get what's the analog of a change in overall energy. It's a tricky thing when you deal with things on a very large kind of cosmological scale. Energy conservation of the kind that one's used to in kind of ordinary physics doesn't quite work the same way. So there's a bit of subtlety when you're dealing with sort of the whole universe. Is the energy of the whole universe conserved? Well, not really quite. Maybe the energy of the universe, the matter plus the gravity, et cetera, et cetera, et cetera. But that's then complicated to define what you mean by the energy associated with gravity and so on. It's all rather complicated. And so on that very large scale, the idea of energy conservation doesn't quite work the same way. But as far as we're concerned with sort of the things that we are capable of observing on the Earth in astronomy and so on, energy seems to be conserved. And the energy being conserved means all these different forms. You can associate a number, the energy number associated with each one of these different ways in which you can have energy, and the total of all those different forms of energy is always constant. Okay, so what does it mean to be running out of energy? Well, I think what that means is that energy, the thing that's really convenient about something like gasoline is that you can just pour it into the tank in your car, and you've effectively got lots of energy that you can make use of just sitting in the tank in your car. It's the same thing with a battery. A battery, there's sort of within that battery is sort of stored up lots of energy. It's kind of like the spring story. It's kind of as if you've got this thing that's the stretched spring, and but it's sitting right in the tank of your car. It's sitting in your battery, whatever, and it's easy to release it by, for example, burning it in the case of gasoline, by putting electrical connections in the case of a battery and so on, letting electrons be pushed by the battery, those kinds of things. It's those are forms of energy where it's really pretty easy to release that energy and have it do something useful for you. So, for example, in the case of the car or something, it might be producing heat in a very controlled way that expands gas that makes cylinders move, et cetera, et cetera, et cetera. So what's really happening is that energy has been sort of packaged up. There's energy is stored in something like gasoline. You can store it in well, hydrogen, things like that as well, or in a battery. You're storing energy in a form where you can easily make use of it. What isn't useful is, okay, so once you've had that energy, eventually the energy is, once you've burnt the gasoline or something, it goes out as a bunch of waste products and heat. Okay, the problem is that heat is not something you can as easily get energy out of. There's a limit to how much sort of organized energy you can get out of heat. So remember, heat is this microscopic motion of molecules. But let's say you want to make your car go forwards. Well, if you could arrange all those molecules, what you're trying to do is get all the molecules in your car to go in the same direction. But just having heat doesn't give you that, because heat, all the molecules are going in random directions. And so you have to have a whole kind of set of machinery to go from the sort of the heat, the molecules going around randomly, to organize that in some way. So you can do that using pistons and cylinders and things moving and so on. And the sort of classic example of this is steam engines, where you're kind of turning heat into mechanical work, into actual motion of the steam engine. But it turns out there's a limit to the efficiency with which you can do that. And essentially the way you're doing it is you have sort of a hot thing and you have a cold thing, and the flow of heat from the hot thing to the cold thing, that the fact that there's a flow kind of organizes the motion of the molecules roughly. And it's that organization that you can kind of latch onto to actually get your steam engine to go forward, so to speak. Because there's sort of a hot thing and a cold thing, as the heat moves, as the motions of the molecules that are sort of all jiggling around in the hot thing and are going much less quickly in the cold thing, as you're kind of moving from one to the other, there's sort of, in some sense, the molecules have to be sort of pointed in the right direction. And it's roughly that you kind of latch onto to kind of go from sort of pure heat to something that is actually organized mechanical work. But the problem is that's not terribly efficient. There's a limit to the efficiency of that. So the sort of energy that's in an efficient form, where it can be readily turned into, for example, kinetic energy, which is a typical kind of energy that we want to have, that's in much shorter supply, because by the time it's just pure heat, it's hard to get back something that is a useful form of energy. So when people say one might run out of energy, what's being said is that the packaged forms of energy, like the chemical energy associated with fossil fuels or something like this, the packaged forms of energy that are very conveniently put in gas tanks and things like this, those packaged forms one might run out of. I don't think one will in actuality, because it's just a question of how far you drill and where you drill and all those kinds of things. But in principle, there's a limited amount of that material, and one could run out of that, and then not have this kind of conveniently transportable and packageable forms of energy. Now, there are plenty of forms of energy that are sort of very that are kind of where there's very large amounts of energy available. For example, nuclear energy, there's vast amounts of that available. The sun is making use, will shine for 10 billion years, just using up the kind of supply of nuclear energy. Where did that energy originally come from? Well, it originally came from there was a bunch of energy that was kind of packaged up into the sun by the fact that the sun was kind of aggregated by gravity took a bunch of material and it squashed it all into the sun. And even before that, there was material in the very early universe that was formed into hydrogen and helium and so on formed into these kinds of materials. And it's kind of the fact that we get to make use of energy from the sun and this nuclear energy from the sun and so on. That's essentially, the sun is a packaged piece of energy that was originally just came from all these different gravitational things being pulled together and making this energy sort of packaged up in the form of a star. By the way, it comes back to things I was talking about earlier about the thermodynamics of gravity and exactly the way in which kind of gravity can organize things which would otherwise be thought of as heat. So gravity will successfully take things which are just sort of blobbing around randomly as heat and sort of attract them together, package them together. So it's kind of doing something, so a little bit the opposite of what I was claiming tends to happen with friction and so on, where mechanical motion turns into heat. It's gravity is capable of sort of reversing that in a way that is still a little bit not well understood. I mean, the details of how gravity works at that level are well understood. What consequence that has for very large numbers of particles and so on is not so well understood. But so I suppose the big picture answer is that we can energy altogether in all forms is conserved, but energy in a form that is useful to carry around is in shorter supply, and you can end up taking all the energy that's useful to carry around and turn it into heat, which you can no longer sort of usefully carry around. But the fact is that there's immense amounts of energy that was essentially left over from the formation of the sun, which was ultimately left over from the beginning of the universe, that we can continue to make use of for a really, really long time. But there's the practical problem of taking the energy associated with the processes that are going on in the sun and converting it to something which we can use. So we might have photovoltaic cells, solar cells, whatever, which are taking light from the sun, produced energy. That light is taking energy from the sun. The light has energy associated with it, and we're taking that light energy and we want to convert it to something we can conveniently use, like electrical energy that we can store in a battery, carry around in our phone or our car or whatever else, and make use of it where we need the energy, so to speak. So that's a rough answer to that. Let's see. Maybe one, two more questions here. Well, let's see. It's a question here from Jamie. How do mutations or radiation effects affect biological evolution? So biological evolution is the main story is biological organisms are specified by programs that are defined by DNA. So DNA is this long molecule that has these different base pairs, A, G, C, and T, and is a sort of a code defined by the sequence of A, G, C, T, T, A, G, whatever it is. 6 billion of those base pairs for humans. That defines a program, and from that program, you construct an organism. And that construction process works by using little chunks of that DNA to make proteins, and those proteins are made of amino acids, and depending on the sequence of amino acids, which is determined by the sequence of bases in the DNA, the protein will be a different shape and have different function. So for us, we have, I don't know, maybe 30, 40,000 kinds of proteins in us that are doing very different things. Some proteins are making the hemoglobin that transports oxygen around in our blood. Some proteins are making muscles, myosin, that makes the fibers in our muscles and so on. These different proteins are making all the different things that make up us. Now, biological evolution is a gradual change of the program of the DNA that is causing organisms to change what proteins they make and eventually change how they are constructed as organisms and how they behave as organisms. So what's happening in biological evolution is that there's gradual errors that crop up, that creep in to these pieces of DNA, there's gradual changes. A T might turn into a C, a G and a G might turn into a single T. These kinds of things. There's little changes to this DNA, and we all have maybe a few million kind of changes relative to the DNA that our parents gave us, so to speak, when we are originally made. When the original replication happens, there's a certain error rate, and we end up with a difference in our DNA from our parents' DNA. And so biological evolution is the story of those changes to the DNA. Sometimes those changes to the DNA will make one a better organism. Maybe that change to the DNA, if one has horns or something, the change to the DNA will make the horns, pointier, let's say. And then if you have pointier horns, maybe you do better in life. Maybe you make more baby pointed horn animals and so on. And so the story of natural selection is, and biological evolution, is that if you are a better organism, better is defined as you have more offspring. And as soon as you have more offspring, your genome is showing up in more places. And so they'll have offspring and your genome will get spread. And so what happens is that changes to the DNA that are advantageous, that give you more offspring, they will get amplified in the population of organisms, because that change, there'll be more little baby creatures which have that change in them, and those baby creatures will be more successful, assuming that's how it's working, will be more successful than other creatures, and then they'll have more offspring, and pretty soon, after some number of generations, there'll be a lot more pointy-horned animals than blunt-horned animals, let's say. And so that's basically the way that works. Now, the question is, what's the rate of mutation? Now, if the mutation rate is too high, the mutation rate is really slow, there won't be a lot of innovation for a long time. It could take, there will be just changing just one or two base pairs. And, it might take, 100,000 generations before you actually generate a pointy horn, so to speak. On the other hand, if you have too high a mutation rate, the chances are you'll end up doing something terrible. You'll end up having the thing have, no head or something like this, because you have the wrong thing being generated from the DNA. So if the mutation rate is too high, there's a good chance that you'll have a disastrous mutation that does not make a viable organism. And so you have to kind of just have the right rate of mutation. You have to have a mutation rate that's not so slow that no innovation happens for a gazillion years, and not so high that you often kind of walk off the path into the mud, so to speak, and end up with an organism that isn't viable. So that's now. There are a bunch of ways in which mutation rates are moderated in biology. So there are situations where the environment seems bad. The mutation rate will go up because it's like things are not the way you were before. You probably have to make big changes to make yourself better because the environment is somehow bad. And that's a phenomenon that happens. There's a certain amount of control that biology has, that you can evolve the evolution rate, so to speak. And that happens to some extent. But you can artificially increase the mutation rate by just messing around with the molecules. So for example, if you use radiation, ionizing radiation, radioactivity, and so on, you can just make the atoms in the DNA, you can just kick them out of place. And so that means that you thought you had an A, but you kicked it, and now it rearranged itself, and it's really turning into a T. That rearrangement often happens through things like proofreading enzymes that kind of try and rearrange the atoms to sort of patch up the fact that something went very wrong with the structure of the molecule. But so when you increase the radiation, you increase the mutation rate, and that can be a thing that is useful. if you're interested in making sort of bigger moves in exploring the space of possibilities. Um, and that's sort of and there are also chemical processes that lead to higher mutation rates. Now, one of the things that can happen is when in tumors are, well, there's both a cause and an effect there. Tumors end up usually with really messed up genetics. Their DNA is really quite messed up. But some of that is kind of after, some of that is a cause, some of that is an effect. But in any case, when you start messing around with genomes, with radiation, for example, or with chemicals, one of the things that can often happen is that you end up going into a place where there are particular aspects of DNA which, if you switch them on or off, can cause tumors to occur, where you have unbounded growth of tissue, rather than, normally when tissue grows in us, for example, once you're, I don't know, once some organ is of the right size, it stops growing. But if you have tumor cells, then they'll just keep growing. They'll just ignore the signals that say you're big enough now. So that's a thing that can happen when you just start messing randomly with DNA. You can wind up sort of hitting those landmines of ending up with tumors developing. Okay, let me see. Maybe one more here. Boy, there's some detailed physics ones. I don't understand that question. Ollie is asking, how size dependent is the universe? Is it possible that we could make a mini galaxy within a controlled environment here on Earth? Interesting question. I think the answer to that is no, for something like a galaxy. I mean, it's a little bit complicated because there are, let me think about this. Yeah, so the issue is the following. Gravity is a pretty weak force. On a scale of planets and things, it's strong enough that it can sort of pull planets together, or pull the Earth to be attracted to the sun so it stays in its orbit, things like that. But most of the time, the force of gravity is really quite weak. So, for example, in space, if you have two spacecraft and they're just sitting, they're going in orbit around the Earth and they're just sort of hanging out, there'll be a small force of attraction between these spacecraft. Or if you have something near the International Space Station or something, the mass of the International Space Station will lead to some gravitational effect, and it will sort of pull the things towards the space station with some force. So an interesting question would be, can you be in orbit around the space station? I don't think that quite works, because there's enough kind of random kicks to things associated with, I don't know, imperfections in the gravity of the Earth, or associated with just some gas that might be left over at the altitude that the ISS is at, things like this, that the pure, it's just gravity that has an effect, letting something, let's say, orbit the ISS. I don't think that quite works. So in other words, the force of gravity, you have to kind of remove all other forces for the force of gravity to be the thing that's dominant. And it's hard to get to the point where you've removed all other forces. And sort of here on Earth, the effort to, for example, measure the force due to gravity, it's not so easy to measure the force due to gravity. Typically, it's done by things like torsion balances, where you have a very precisely sort of balanced thing that you're moving back and forth, and you're looking at a very subtle effect that moving it one way versus another has the consequence of having a gravitational effect. But it's pretty subtle to actually detect that gravitational effect, and it's hard to have some sort of thing that is affected only by gravity. Now, having said that, there can be equations that are like the equations of gravity, and you can have things in fluids and things like that that sort of behave as if they're behaving according to forces due to gravity, but it isn't really gravity. It's just that the mathematical equations are the same. So the same thing happens when you think about black holes. So a black hole occurs when there's a very large mass in a very small volume, and it kind of produces such an extreme amount of gravity that in the traditional view of the way things work, that you get kind of an infinite curvature of space. In our models, it's a little bit clearer what's happening, but roughly, very large mass, very small volume, you make a black hole. You could have a very tiny black hole. If there was one that if somebody made a very tiny black hole somewhere in the universe and it's zipping across the universe and eventually hits the Earth, it's kind of bad news for us. But you could just imagine, and people sort of worried that maybe something we'll do will make a very, very tiny black hole and it'll suck the whole Earth in, and it's bad news, so to speak. For example, people were worried, a few people were worried when these new particle colliders were going to be put online maybe 20 years ago now. The thought was maybe colliding these particles in this way that hasn't really happened since the beginning of the universe, that if you do that, you will sort of crush matter to the point where you will have enough density of matter to make a black hole. And so people were like, don't start that particle accelerator, it might make a black hole. This was not very plausible from a physics point of view. It was very far away from where one would expect to be able to form a black hole. But in principle, we don't know how to do it, but in principle, you could make a black hole that's sort of your very, very tiny black hole that you could just, keep in your closet type thing. It would be hard to keep, by the way, but it would be, in principle, you could have something that was sort of local like that. But then the mathematical equations that govern how things work near black holes, and near a black hole, you can have matter that's kind of swirling around in a disk around the black hole, an accretion disk, and so on. You can have those kinds of effects in things having nothing to do with gravity and nothing to do with black holes, things in fluids and so on, and with electromagnetism. It's the same mathematical equations, but from a different origin. And so you can kind of have the analog of some of these phenomena, but they're not really the phenomena themselves. And so I think the main point about sort of scaling of things up and down is things like atoms are a definite size. Things like and it's that definite size, their definite size, their definite mass, their definite electric charge, and so on. Things like that kind of determine the overall scale of material that we can deal with. Now, if you had a different kind of thing, if we weren't dealing with atoms and protons and those kinds of things, then you could sort of change the scale of everything, and then you could maybe have a galaxy in a marble, as that scene at the end of the Men in Black movie kind of portrays. But that's not something that, given the actual masses of atoms, the actual force of gravity, and so on, that's not something you can achieve. Yeah, so it doesn't scale quite that way. Okay, let me just see. There's a question here. Actually, there's a question from Chocolate. I can answer this one. Is there fusion going on inside a black hole? We don't know. And here's the thing. The definition of a black hole is everything falls into it, nothing comes out. So light, for example, is pulled into a black hole but never gets out. There's a so-called event horizon that means that effects outside the black hole can affect things inside the black hole, but things inside the black hole can never affect things outside the black hole. At least that's true to a first very good approximation before you start worrying about effects from quantum mechanics and so on. But and there's we could talk about that too. But in an ordinary sort of story of a black hole, things go in but nothing comes out. So whatever's going on inside a black hole, we don't know what's going on inside a black hole. Now, when black holes are formed, like the one at the center of our galaxy, or the ones that come about when stars collapse and so on, everything that was in that star is getting crushed inside the black hole. And the and so stuff is going on inside the black hole. It's just we never get to see what's happening because we're only seeing things on the outside and nothing, no light or anything else is escaping from the insides of the black hole. So in some sense, it's like, well, there may be stuff going on, but we don't know what it is. Now, what's actually going on there? It's a good question. If when if you take a star and you kind of crush it down to a tiny size, what's it like? In other words, we could, if we were in there, if we were sort of part of what was sucked into the black hole, what would we experience inside the black hole? Good question. It's so the one of the things that's sort of a downer about black holes is you don't get to experience stuff for very long because in effect, the structure of space-time is sufficiently distorted that inside a black hole, basically time stops. Actually, there are different kinds of black holes. The simplest kind, time stops. The other kind, space stops. So the kind where time stops, non-spinning black holes, essentially what's happening is any entity inside the black hole will, within a limited time, will just stop. Time will stop for it. Nothing, if it was thinking, so to speak, it will be frozen in some state and no more thinking will happen. If it was a clock, it will be frozen and no more clocking will happen, so to speak. So in a sense, one's experience of what's happening inside a black hole is very limited. It's because time will always stop for one after a limited period. Or alternatively, in spinning black holes, space will stop. One will be continually repeating oneself over and over and over and over again for infinite time, but one will never be able to sort of get out of this infinitely small region of space. Now, sort of before you get to the moment when time has stopped, what will you experience? What will it be like in there? I'm not sure. What happens to matter when you crush it a lot? For example, when stars that aren't quite big enough to have enough gravity to crush themselves into black holes, when they kind of contract down after a supernova explosion, they'll make neutron stars. Neutron stars are like giant atomic nuclei. They're like what you would get if you had a single atomic nucleus that's 10 kilometers across. They're made of neutrons, just neutrons, and they actually are superfluids where the neutrons are kind of flowing next to each other in all sorts of ways, but it's basically a big clump of neutrons that's like the nucleus of an atom, a giant atomic nucleus. But it is also something where if you were to move inside it, there would be no viscosity, there would be no friction to moving. You'd move around, you'd start the neutrons moving as a result of the motion that you put in there, and that motion wouldn't dissipate, at least not at any reasonable speed. So it'd be a very, very weird kind of material. Now, does fusion happen? Well, fusion doesn't happen in neutron stars because it doesn't have there's no way to end up with something sort of what you've got with a neutron star is as compact as any kind of atomic nucleus type thing is. And so fusion comes when you have nuclei like hydrogen nuclei that can sort of be more compact, give out energy and sort of become more tightly bound by connecting, by sort of clumping themselves together to be helium nuclei. And that doesn't happen. By the time you've got neutrons, it's as clumped as they get, so to speak. So my assumption would be that, well, it's complicated because my assumption would be that you'd end up with something much like neutron star material that doesn't have fusion actively going on in it. It's an interesting question if there was pressure from material inside the black hole, what effect would that have? Well, it has no real effect. On outside the black hole, it has no effect. The force of gravity is like a container that is it's an infinitely strong container. So whatever pressure there might be in there, it's not going to have an effect outside the black hole. If there is pressure, the only thing it will do, I think, is to make the kind of singularity in space-time kind of be such that maybe time will stop more quickly for one if there's pressure there. I think that's the only kind of only kind of effect. But it's a yeah, it's an interesting question. I mean, unfortunately, in most, well, by the time, so as I mentioned, black holes, mostly things go in and they never come out. But there actually is an effect called Hawking radiation, where you can have effectively energy coming out of the black hole. And it happens, well, it's kind of a tricky effect. The easiest way to understand it is in the vacuum, where you think there's nothing in sort of between galaxies or whatever else, but you think there's just one hydrogen atom per cubic meter, for example, between galaxies. But actually, the vacuum is a very active place. In our models of physics, the vacuum, the actual structure of space is knitted together by activity in the vacuum. You have this kind of giant network of all these different atoms of space, and they're all being sort of the network that connects these atoms of space is continually being rewritten, and it's that process of continual rewriting that kind of makes space be coherent. If there wasn't that continual rewriting happening, then something that happens in one place of space would never have an effect on something that happens in a different place in space. So there's all this activity happening in the vacuum. In our models, it's really this activity of the progressive rewriting of the network and the ability to transmit effects from one place in space to another. In standard quantum field theory from the last 100 years or so, it's that one's forming particle-antiparticle pairs, electrons and anti-electrons, positrons, protons and antiprotons. They're continually in the vacuum. Those are popping into existence and then annihilating each other again in very short amounts of time, and we don't ever notice that. I think actually our models of the structure of space are a little bit clearer about what's going on, although you can kind of see it as an infinite collection of particle-antiparticle pairs getting formed and annihilating again. But I think it's really more just that there's a structure of space, and space has to have activity for different parts of space to have an effect on each other. But in any case, be that as it may, what happens when you think about it as particles and antiparticles forming is you can have this little fluctuation where a particle-antiparticle pair forms that's about to annihilate, but before it annihilates, one of those particles gets pulled into the black hole. And so then the other particle, what's it going to do? It's all on its own. It can't annihilate again. And so it ends up being produced as radiation that looks like it's coming from the black hole. So it's all been a bit mysterious how things can sort of form into black holes, everything's packaged inside, and then things come out again. And somehow you're kind of taking what was a certain amount of information about the black hole, and you're having more information coming out and all the configuration of these particles and so on. I think the real story is actually something perhaps even more bizarre than that, which is the following thing, that as you fall into a black hole, one of the things that, if you watch a spacecraft falling into a black hole, we don't get to do that because black holes that we know are really far away and so on. But let's say you were watching a spacecraft falling into a black hole. From you, far away from the black hole, the spacecraft will just become frozen right on the surface of the black hole. You'll never actually see it go inside the black hole. To the folks inside the spacecraft, they'll say, oh, we just went inside the black hole. Actually, the only way they'll know that they went inside the black hole is that the signals they send to other people will never get an answer. The signal, it'll take longer and longer for them to get an answer, and eventually they'll never get an answer. By the way, in some sense, as they fall into the black hole, they'll see the whole future of the universe, because effectively the fact that they what for them is a limited amount of time, for everybody else is an infinite time. So in their limited amount of time, they get to see the sort of infinite future of the universe. Okay, so that's one sort of way of thinking about things. They sort of, to the outside world, they freeze on the surface of the black hole before falling in. And I think what happens is that when you're the way things work in quantum mechanics, boy, this is going to get us into another thing which I probably shouldn't get into now, but in quantum mechanics, the sort of key idea is that there isn't just one history for the universe. There are many different paths of history that branch and merge and so on. And when our experience comes from sort of knitting together those branches of history so that we conclude that one definite thing happens. But that process of knitting those things together so we come up with a definite conclusion, that essentially happens infinitely slowly just when you get close to a black hole. And I think what happens is that you kind of don't, as the black hole forms, there's the kind of the what's going on question. If you're kind of an observer near the black hole, you get into this state where you can no longer kind of make a decision about a definite thing happened. You're always stuck in this kind of quantum superposition of different states. You never get to say, oh, I know what happened. You're always stuck in this, I don't really know what's happening. There's lots of different things that could be happening. And I think that kind of resolves sort of, there are a bunch of paradoxes associated with sort of formation and then disintegration of black holes. And I think that sort of resolves those kinds of things. All right, there's a comment from Spare Parts that closet-sized black holes will explain the missing socks. I think that's probably a signal that we should wrap up for today. It's a fun thought there. And thanks for joining me, and I will see you another time. Bye for now.